right, so this is Unit 7 progress check for your response part A. So this one, there's just one question on this first part. It is a non-calculator question. So we've got the setup here that says a large vat is initially filled with saltwater solution. Solution with a higher concentration of salt flows into the vat and solution flows out of the vat at the same rate. The number of pounds of salt in the vat is modeled by the function A that satisfies this differential equation. So we have dA by dt, so that is the rate of change of the amount of salt like per minute in respect to time. So that's our differential equation. And then it says that at time t equals 50, the vat contains 50 pounds of salt. Sorry, at time t equals 10, so that's our initial condition. So differential equation with an initial condition. So let's start with part A. Part A says, write an equation for the line tangent to the graph of A at t equals 10. So anytime you are told to write the equation of a tangent line, I like to have you guys set this up. And then for this one, we have a change in variables. So A is the amount, so that's going to be your y variable. And then t is time, so that's going to be your x variable. So we set that up. And they say at t equals 10, so we know that part. We're given an initial condition. We're told that at t equals 10, A is 50. And then the slope would be the derivative at that point, and the derivative is given by this expression right here. So we can sub that value in. So dA by dt at that specific time is 6 minus 0.02 times A. So notice this expression only has a spot for A. It doesn't have a spot for T, which is fine. This just means that the rate of change is based on the amount rather than being based on the time, which is pretty normal actually. So A, we are going to sub in 50, which is the value at that time. So 0.02 times 50 ends up actually being exactly 1. Like if we kind of work through 2 times 50 is 100, and then this decimal place would move over twice. So this just ends up being 6 minus 1, which is 5. So the 5 gets subbed in here. Remember for me, for the AP test, it does not matter if you move beyond point slope form. You can just leave it in this form like this. Letter B. Letter B says, show that A of t equals 300. So this lovely expression right here satisfies the differential equation with the initial condition. So we're going back up here. When it gives us that A of t, that means that we are doing the separate, integrate, isolate. So we're going to be solving for A instead of solving for y, and we've got our initial condition. So start with our differential equation that we have up at the top here. I'm going to separate it. This whole entire quantity needs to move as a quantity over to the left-hand side. You can't separate by using addition or subtraction. Otherwise, if we add this to one side of the equation, we would end up with 0.02a plus dA, and you're not really supposed to have plus a differential, it's just times a differential. So this whole quantity would have to divide over to the left-hand side. So we have 1 over 6 minus 0.02a with the dA, and then we don't have anything over here with the dt. That just means there's technically a 1. All right, so this is our setup here. We are going to integrate both sides of the equation. When we integrate the left-hand side, the a in the denominator means that we're going to be doing a natural log. So it's going to be natural log of the absolute value of 6 minus 0.02a. But then because there is this nested expression, we have to undo what that chain rule would be doing. So you could do a formal use substitution. You don't have to if you don't want to. What I like to do is just kind of take this as a correction factor and balance it. So if you did do an official use substitution, I can show you this over here, you would use this expression as your u. Your du would be a negative 0.02 dA. And then since there isn't a 0.02 dA in here, you would divide both sides by that. So keep in mind that 0.02, this is actually negative 1/50th dA. So to solve for a du, we would multiply both sides by negative 50. So we have negative 50 du is equal to dA. So this is going to have a negative 50 out front. So I do my u substitution. This ends up being the natural log of the absolute value of u, and then we have a negative 50 du. So this is my antiderivative of the left-hand side. The right-hand side, if there's technically just a 1 there, the antiderivative of 1 would just be t plus c. We have to have a plus c there. We can't forget about it at this step. So we've got this as our initial condition. Where did that go? It is up here. So we can plug this in right now and solve for c, or we can wait until later, plug it in then. Truly does not matter. Let's just get the a by itself at this point. So we are going to divide everything by negative 50. And we know based on this that dividing by negative 50 would actually be the same as multiplying by negative 0.02. So that's what I'm going to do on the right-hand side. And the c is just an unknown constant, so we're going to leave it as just a c. We would then exponentiate both sides like this. Left-hand side is now just the absolute value of this expression. Right-hand side, we use that little property we've been talking about where we have addition within an exponent, so we can separate it out like this. And then this is still just a constant. So it's not the same constant, but I can say this expression is just multiplied by a constant, and I'm going to put that constant first. Again, I'm just using c as an arbitrary placeholder. This c and this c do not have the same value. I can drop the absolute values by making the other side plus or minus. I'll figure out whether it's plus or minus when I work with my initial condition. But then subtract this 6 from both sides. And then divide both sides by negative 0.02, and dividing by negative 0.02 is the same as multiplying by negative 50. So multiply that by negative 50, multiply this by negative 50. When I multiply this by negative 50, the c would still just be a constant. The plus or minus would still be there. Multiplying by a negative technically changes plus or minus to minus or plus, but obviously that doesn't make a difference. And then here is our constant right here. We don't have to multiply it by 50 because I still haven't actually solved for it. It's still just an arbitrary constant. So that is my solution for A. Then I have my initial condition right here that I can plug in. So 10 gets subbed in for T, 50 gets subbed in for A. So when I plug a 10 in right here, I end up with negative 0.2 instead of 0.02 because I multiplied that by 10. So now I'm going to solve for C. So I can subtract the 300 from both sides. So when I subtract the 300, I get negative 250 equals plus or minus CE to the negative 0.2. And then I am going to, let's see, divide both sides by this e to the negative 0.2. And then I get my value of C. All right, so it's either a positive or negative, and I will figure that out when I go back into my original equation. So I have A equals 300 plus, so now I'm subbing this value in right here. So plus or minus, so that kind of takes care of the negative. Okay, so I'm going back into this expression right here, and I replaced this C right here with this value that I just solved for. So you're supposed to just be proving that it matches what we started with up here. So we're super close. Like we've got the 300 right here. There's the 250 that you see right here. Here's what they did to get this to actually match what we have up here. I have a negative exponent in the denominator, which is a little bit weird. So I'm going to move that up. So it's going to turn into 250 times e to the positive 0.2, and this gets multiplied by e to the negative 0.02t. So two separate pieces that are being multiplied together like that. I'm kind of in a position like this where I know I can add those exponents together. So I add the exponents together. I have the 0.2 plus negative 0.02t. So I'm super, super close. All I have to do is determine whether it's the positive or negative, and that depends on your initial condition. So this tells me when I sub in 10, I want to get 50. So if I sub in 10, the 10 goes right here. This becomes 0.2, and then I have 0.2 minus 0.2, which would be 0. E to the 0 is 1. 250 times 1 is obviously 250. So to get 50, instead of being 300 plus 250, it should be 300 minus 250. So my final answer, I end up choosing the minus from my two options. And then if you look at your original problem, this is actually the exact equation that we were supposed to come up with. This equation that I have right here is exactly what was given to us at the start of the problem. All right, so I'm looking back at my problem and I actually just noticed something from part A that we were supposed to have done. Part A was a tangent line, and it said we were supposed to use that to approximate the number of pounds at t equals 12. All you do with that is you take this tangent line and you plug in t equals 12, and it's supposed to give you an approximation for A. So this right-hand side, 12 minus 10 is 2, 2 times 5 is 10, and so you have A minus 50 is equal to 10. So add 50 to both sides, and we end up with 60, and 60 is given in pounds. So that's the second part to letter A. My apologies for missing that initially. So look at letter C now. It says the flow of solution is stopped, and the solution is drained. The depth of the solution is modeled by a function h that satisfies this differential equation. Okay, so we've got that differential equation. It says h of t is measured in meters, t is the number of minutes since draining began, and k is a constant. So they give us two different initial conditions. They tell us the depth is 16 meters at t equals 0. Okay, so h of 0 is equal to 16. And then they tell us that it's 4 meters at t equals 30. Okay, so two initial conditions, and then it says what is h of t in terms of t. So we're trying to solve for h. We're going to have to solve this initial condition first, which means we're going to get the h by itself, start by separating everything out. So the dh has to be on the left, so this square root of h is actually going to become 1 over the square root of h. So I'm going to write that as h to the negative 1/2 on the left-hand side. Equals, I'm going to keep this negative k on the right. Keep in mind that that is just a constant. So I can integrate both sides, and then I'll end up trying to solve for h because we're trying to find h of t. So this exponent pops up to a positive 1/2, and I divide by that exponent. That's my antiderivative on the left. On the right, if this is a constant, the antiderivative is negative k times t, and then I always have a plus c on the right-hand side. Next, I'm trying to solve for h, get that by itself. So start by dividing everything by 2. Now this actually does need to get divided by 2 because k is a constant. We just haven't figured out what it is yet. So then this plus c goes right here. And then this is the 1/2 power, so what you do is you square both sides of that equation. All right, so square both sides. We get h is equal to this whole quantity right here squared. So that is my h of t so far. I don't know k and I don't know c. That's the reason why I have two variables over here, because you need two variables in order to solve for two constants. So I'm going to sub in 0 for t and set it equal to 16. So subbing in 0 for t would make this whole thing 0, so it's just c squared. So that means that c can either be plus or minus 4, and I'll come back for that in just a moment. Then go back to my original. So that's where I'm at so far. The second condition they give me is that when I sub in 30, I'm supposed to get 4. So negative k over 2 times 30. So 30 is going in for t. Divide that by 2, I get 15. So I have a negative 15k plus or minus 4 quantity squared. Okay, so I've got a little bit of solving to do here. Let's start just going under the assumption that it's positive. All right, so let's square root both sides. I was trying to solve for k. So take the square root of both sides. When I square root the left, I now get another plus or minus on the 4. And that is equal to negative 15k plus or minus 4. Okay, so this one, if I would either like add or subtract the 4 from both sides. So we've got the plus or minus 4 on both sides. So what that means is that k is equal to 0. Okay, so that, if that gets subbed back in, if k is always 0, then t would just be 0. So let's actually try that again. If this is either plus or minus, let's say that this is plus and this is minus, I could put that over to this side, and that would give me an 8. Because like if this is a -4, I would add it to a +4. So I could have 8 here. Or if we think like this could be a negative and this could be a positive, I could subtract that over. So this could either be positive or -8, or it could be 0. Probably not 0, because that would get rid of my entire equation. So let's say it's probably going to be plus or minus 8. So divide both sides by 15. So I get either plus or minus 8/15 is going to be my lovely value of k that I could sub in. So let's plug that back into this equation. So negative k would be 8/15. That is multiplied times t plus c. And so the 15, or the c we figured out, was either positive or -4. So that is my expression. This could be either positive or negative as well. So we know that when I sub in 0, I'm supposed to get 16. We know that when I sub in 30, I'm supposed to get 4. So if I sub in 0, squaring that would give me 16, whether it's positive or -4. And then if I get 30, plugging in 30 for t would again give me 4, whether I have a positive or negative. So this, I think, would need to be either both the positive version or both the negative version. So let's just make this easy on ourselves and say that these are going to be the positive version.